for this opportunity. And this talk is about envisioning the future of solar system exploration. I am Prof. Banerjee, and I work at Physical Research Laboratory. And as was told by our organizers and Dr. Das during the lecture last week, the contents of this lecture must be emphasized that they do not represent the official future plans of ISRO. All right, so basically, this lecture will give you first some details about the solar system, and then I will talk about some very important discoveries which have been made by recent missions, including our own missions, Indian missions. And finally, I will throw some light on future questions which need to be explored in future orbiter, lander, rover missions to the inner solar system bodies, and I hope in future outer solar system bodies and also the asteroid belt. So solar system objects range in size from a few microns dust to giant planets. And the information exists at all scales about the origin and evolution of the planets. And I'm sure you're familiar with the definition of the Astronomical Union, which changed in 2006, that a planet is defined as an object which is in orbit around the sun. It's sufficiently massive and has spherical shape, and it has cleared region around its orbit of large debris. So dwarf planets have the first two properties, but they do not satisfy the third criteria. So therefore, Pluto became a dwarf planet, just as Ceres is a dwarf planet. And then you have asteroid belt and the Kuiper belt objects, which represent residue from planet formation process and have undergone thermal or chemical processing. So this is showing you some, physical properties of the planet and dwarf planets, and you can see that the various radiuses, mass, bulk density, semi-major axis, gravity, temperature, and orbital periods are listed here. So the inner solar system is represented by the asteroid belt and Mercury, Venus, Earth, Moon, and Mars. And then, of course, you have these dwarf planets or asteroid belt constituents, for example, Ceres. Okay, so the densities are bulk densities, and you can see a big difference in the density between that of the inner solar system bodies, which are rocky bodies, and the outer gas giants, or the ice giants, the gas giants being that of Jupiter and Saturn, primarily composed of hydrogen. And you can see a difference in density, whereas that of the ice giants, you have Uranus and Neptune. And also there is a difference in the mass of the inner and the outer solar system bodies. If you look at other particular bodies of interest, particularly where there is the possibility of life, which has been raised. One is, of course, Mars, where there's been a lot of work. But you can see an object, a satellite of Moon, which is listed here, Enceladus, which has a mean radius of 252 kilometers. And its bulk density is 1.6. And there, Enceladus, I will discuss later, there was the Cassini mission, and it basically found molecular hydrogen in plumes, okay, which I will show later, plumes arising from Enceladus. And this was basically evidence. This showed that there are hydrothermal processes occurring, and therefore life may exist there. And Titan has, of course, there's been methane discovered there as well, and that also I will discuss. So many of these objects are of great interest, and exploration has begun. Planetary exploration has begun with Chandrayaan-1, as you all know, and then this has been discussed by Dr. Das and then by Megha Bhatt and others. Then you had the Chandrayaan-2 mission and the Mars orbiter MOM mission, the first Mars orbiter mission, and then Chandrayaan-3 mission, all of which have been very successful, both in terms of engineering aspects and science return. But many, many discoveries are yet to be made by ISRO and other space agencies. And you can see there are so many systems, there are many things to be learned, and this I will discuss in a few minutes from now. So the surface temperatures and magnetic fields are listed here. You can see significant magnetic fields for that of the Earth, and then Jupiter. So, and then of course Saturn and Uranus and Neptune, and the others do not have, they have remnant magnetic fields, minor magnetic fields. Mercury has a larger magnetic field than that of the other inner solar system objects, with the exception of Earth. And it is listed at 300 nanotesla. Venus has a huge pressure, 93 bar, one can see, compared to that of the Earth. But the sizes, if you had noticed, is quite similar. So it's interesting to speculate how two similarly sized objects evolved in a different manner, and how the atmosphere of Venus, which is 96% carbon dioxide, so primarily dominated by carbon dioxide, how did it evolve to its present state? And so there have not been that many missions to Venus, but now several missions are planned. And as Dr. Das mentioned earlier, India is also planning an orbiter mission to Venus, which will look at some of these questions, answering some of these questions. And of course, then you have other missions which are planned by NASA as well. So you may ask how the solar system formed. So 4.5 billion years ago, we know that the solar system has formed from a dense cloud of interstellar gas and dust. So you had a giant molecular cloud, which basically collapsed due to the shock wave of a nearby exploding star. And then you had from this emerged the solar nebula, spinning and swirling mass of material. So therefore, in that, you first have the protoplanetary disk, and then you have the proto-sun, and you have a lot of accretion of material, and then some of the material accretes to form, firstly the sun forms, and then out further, you have formation of planets. And the remnants of the planets, planetesimals, I should say, basically are the constituents of the present asteroid belt, which forms, which constitutes of materials which did not form a planet. And then the others are also there. Other planetary objects include comets, which are visitors, and some of them you would have seen, meteorites, and then finally when they fall, they're called meteorites, and moons. So all these objects have to be studied, and many investigations have been done on meteorites, particularly which have terrestrial, which have fallen on the Earth. But missions are, as you just heard from Professor Sharma, missions have their own limitations. So therefore, you cannot have too many missions, and they're expensive. And there is a long there's a long time. It takes a long time to develop a mission and then make it successful. So nearest to the sun, only rocky material could stand the heat in the solar system. And therefore, the inner four objects, Mercury, Venus, Earth, and Mars, are terrestrial, and they have rocky surfaces, whereas ice, liquid, or gas settled in the outer solar system, and therefore you have the gas giants and the ice giants. And this is general information again about the solar system. So let me just highlight a couple of points which you may not be aware. So meteorites are mostly originating from the asteroid belt, but there are very few asteroid-meteorite connections made as yet. One of the examples, which I will show you, is the link between the HED group of meteorites, the Howardites, Eucrites, and Diogenites, and 4 Vesta. Okay, so that 4 number is basically, that is used for designating planets in order of their discovery. So some meteorites are derived from asteroids, and they have experienced differentiation. So differentiation, a meteor, the heat of accretion melts, or radioactivity which is present, for example, aluminium-26 in the early solar system is responsible for heating, is a heat source, and therefore you have had melting, and this results in differentiation in large asteroids. And so it is a differentiated body. Okay, so there's a term called differentiation, which is also relevant in the case of Moon and other objects and other planetary objects and Earth as well. Now, chondrites are, they contain spherical chondrules. Okay, so of olivine and pyroxene. So the olivine and pyroxene are ferromagnesian minerals, okay, and chondrites are a type of meteorites, okay, and they have been studied, and there are various kinds of chondrites. I will not go into detail in this lecture, but that is one way of knowing about the early solar system, okay, by studying meteorites. And I will just have 2 slides which I will discuss later. Then a group of meteorites, as I've told you, is linked to a parent body, but we would like to establish this meteorite-asteroid links, okay? And that can be only done if there are additional missions from various space agencies, including our own ISRO, to these meteorites, and wherein they collect the spectra and may perhaps collect samples from the asteroid and match the spectra with that of the meteorite spectra, and also the elemental composition as well. And that definitely tells us and will establish that a certain group of meteorites has come from a particular asteroid. So this is one of the things which is yet to be done, and has been only pursued for a couple of cases. Okay, and then you have irons as well. So planetary bodies go by accretion of grains, okay, centimeter-sized objects, kilometer-sized objects, and then kilometer-sized planetesimals, and then more collisions and more accretion resulted in bodies of a few thousand kilometers, and that is comparable to size of a planet. So some fundamental questions to throw at you at a very early stage is why life has only originated on Earth as we know now? How did Venus acquire its present dense atmosphere? You saw the pressure, 93 bars. So how did that happen? Is it because of the greenhouse effect? But the greenhouse was a runaway greenhouse effect, not the greenhouse which we are seeing. There is a greenhouse effect on Earth, but the order of temperature increase due to the increase in CO2 in our atmosphere is only, the average increase is about 1.5 degrees, okay, and not the temperatures which are encountered on Venus, which make a mission to the surface of Venus very difficult. Why Mars has a very thin atmosphere and why Moon has no atmosphere. All right, so the other things I have explained. So let me come to this slide. And when this lecture was given, the previous lectures which I have given for the START program relate to solar system in interaction to the solar system, but this was something different. So therefore, I started assimilating facts, and I found that if you have 5 basic themes, then most of the questions relate to these themes. Okay, so the origin and evolutionary history of a planet or a satellite. We would like to know that. Okay, and for that we need measurements and detectors which have to be flown on board an orbiter for a synoptic view, or a lander or a rover for looking at the surface, for investigating the surface of the moon or the satellite or the planet or the asteroid. Or we would like to bring samples back from the moon and other objects. And of course, the primary interest at the moment for us is that of the moon. Okay, and it is also of interest. Let me tell you. I will show the last slide. The second last slide will show you all the missions which are planned or which have been realized till now, or which have failed. In fact, some of them have not been successful entirely, but you will see that there have been very few sample return missions, and all of the space agencies wish to bring back samples from the moon to learn about its early history, and also all the other objects. Climate is relevant in the case of Mars, okay, and Venus, and some of the satellites. So how did the climate change through time in the case of Mars? And then if you have a climate which is not hostile, which is similar to that of the Earth, if you have resources, if you have volatiles, if you have objects, if you have water or objects, carbon, which is present, organics which are present, then possibly some bodies such as Mars could have had life in them. Okay, so which are the habitable bodies in the solar system? So this is my third theme. My fourth theme is internal structure. So Moon is still thought to be non-seismic. On Earth you have the plates, and you have earthquakes, tsunamis, which are the waves, which follow the earthquakes. And but on Moon, for example, earthquakes, you have a very mild seismic activity. It is not known for tectonics, plate tectonics. Okay, and similarly that of Mars. So we would like to know the internal structure of the planetary objects. And the last circle relates to themes of volatiles and resources. In situ resources are extremely important. People are already planning how to, they're thinking about ideas as to how to mine an asteroid. And there are works in the literature which you will see which look at asteroid mining. Okay, so the resources are there, even on Moon. How do you utilize them? Okay, and then you have volatiles as well in polar regions on the Moon. So what is the distribution of these volatiles? Where are these volatiles? Okay, are they only in the permanently shadowed regions, or in other regions as well? So actually, I mean, if you think about it, only we know perhaps information about we know at orbital scales we know, you know, but or from an orbit you're looking at resolutions which are not comparable to what you see when a geologist moves on the Earth and actually sees features. So perhaps that will be feasible in the future when the first man arrives from India on in space and subsequently on the moon. So you can ask what are the options, okay? So I put down some here, orbit, and these are not, these do not include everything, let me tell you. So orbiting mission, which gives you a synoptic picture, and these include topography, chemistry, and mineralogy, and these were the three main things which were aimed from Chandrayaan-1 mission of ISRO. And then you have lander rover missions, and one new thing, for example, in Mars, you have had the InSight mission, you know, from which looked at the interior structure from NASA. But seismic experiments will become very relevant because you wish to study what is there within the planetary body and also the internal structure and the core. And then sample return mission. And besides that, of course, you can also look at features and tell about, if you see, once you see the geomorphic features, not that I shouldn't say geo actually, but that term is still used. Once you see the morphology, you can tell about what has happened on the planet through its history, okay? Has ice flowed along the surface, because that will create certain features which are different to that of the features which are created when a river incises land, okay? So all these features and that water on Moon and Mars are extremely important themes at the moment. Sample return missions include dating. Once you get the samples back from the object, can you pursue dating? Minor and trace element chemistry and isotopic effects as well can be studied, and these are all complementary. Now, how do you perform all these studies? So if you look at the electromagnetic spectrum, which is shown here, so entire region of the electromagnetic spectrum is there for basically understanding various features of our solar system. So if you look at microwaves, okay, you can have radars, you know, L and S band radars, okay, in the gigahertz range, 1 to 2 gigahertz, 2 to 4, which look at subsurface features, including the possible presence of ice. Then the infrared looks at surface mineralogy and also water, as you know about the discovery on Chandrayaan-1, M-Cube. And then you have X-ray, which is looking at near-surface elemental chemistry. And you all know about APXS, the alpha particle X-ray spectrometer on Chandrayaan-3, which is now providing ground truth, and also it has told us about the fact that some material of South Pole Aitken Basin has come into this region, okay, into the landing site region. And then you have the surface mineralogy, which is also coming from the visible area, and then elemental composition can also be determined from gamma rays. So these are the ways, and you need detectors in different regions, okay, which actually gather the signal and tell us information about the planet or the satellite. So this is just to show you. So this is just to show you different types, okay, of missions. So I hope you I hope you know that what is shown on the top left-hand side is the Chandrayaan-1 orbiter. And then Chandrayaan-1 was an extremely successful mission, the first Indian orbiter mission to the moon. And then you have the Sojourner. That is the picture which is below the Chandrayaan-1 orbiter, and that That is basically, that was flown to Mars by NASA in 1997. And that was the first wheeled object on Mars, to move on Mars, and on any planetary body other than Moon or Earth. Okay, that was basically the Pathfinder mission, to Mars, which renewed a lot of interest in Mars. And then on the right-hand side, you have the sample capsule. Okay, where the credit is given. This is from Dante Loretta, the reference, and this is basically the this is a sample, the mission to Bennu. This was the Rex mission, okay, Rex mission to Bennu from NASA, and that is the sample return. So it returned about 120 grams of material, if I remember correctly, of what is shown on the left-hand side, and that is the Bennu, a carbonaceous chondrite. So that means it has carbon, more carbon than that in other meteorites, which are stony meteorites. Okay, so carbonaceous chondrite mission. So you can see different examples here of a rover mission, rover lander. That is a rover, of course, or an orbiter, or a sample return mission here. Okay. Srirag, I began at 4:30, right? Is that correct?
Yes, correct.
Okay. Okay. So 25 minutes have elapsed, and okay, maybe I have to speed up. But there are other ways. Okay, once you bring back the samples, there are other ways and instruments which help us understand how the early solar system had formed and evolved. So for this, you need primitive meteorites. Okay, meteorites are basically they have come from asteroids, but we don't, as I said, that we don't know the link. So they've come from asteroids, and also sample return objects. And for that, you need mass spectrometers, radiation detectors. So I have listed some examples for solids, for measuring stable isotopes. You can have ion microprobe, thermal ionization mass spectrometers, nanosims. Okay, so the resolution is better there. ICP, inductively coupled plasma mass spectrometer. Okay, and then you have gaseous elements, the noble gas mass spectrometer. For isotopes, let me come to elemental characterization, elemental composition. So you can have X-ray fluorescence, ICP-MS, and then EPMA. Okay, electron probe analyzer. Then for isotopes, you can have detectors, basically a gamma ray detector, a beta alpha detector. So some examples, okay? So these are called stardust telescopes, and because they can be used to study stardust, pre-solar grains, okay? So you can see a picture of nanosims, and PRL, where I belong to, has a nanosims. And this is used for measuring major or minor element ratios, and at a higher scale than an ion probe. And then you can have also resonance ion and mass spectrometry, which is looking at trace elements, and electron microscopy, okay, TEM, which is looking at nanometer sized structures. Now I will come to discoveries, and then I will conclude with questions. Okay, so Mercury. Okay, now remember, Mercury is supposed to be very close. It is close to the sun. Okay, now Mercury is still a volatile. It has been found to be a volatile rich world. So this picture is showing you a result which was published in Science, and this is a result from Messenger, and you can see the GRS measurements. So GRS is basically a gamma ray spectrometer. Okay, so you can have a scintillation gamma ray spectrometer, or you can have a semiconductor-based, germanium-based gamma ray spectrometer, and that looks at gamma ray signals. And by measuring the signals from the planetary surface and gamma rays, we're talking about basically a signal which is looking at up to tens of centimeters inside the surface, as opposed to X-rays, which are looking at microns. So this is a plot of potassium versus thorium, and potassium is a volatile. So volatile elements that evaporate at moderate temperatures are observed in higher concentrations on Mercury than that on the Earth, and are comparable to that of Mars. Okay, and therefore, and also high abundances of sulfur and iron suggest that they form with less oxygen. Okay, because of, I mean, you have to balance the elements basically. Okay, so so therefore you have volatile in a body which is very close to the sun, and this was a big surprise. And this is a picture from this is from O'Rourke et al. And this shows you Venus in various wavelengths. Okay, so you know this is, so if you look at multi-wavelength, you've heard of multi-wavelength astronomy. This is a result from studying a planetary object using multiple wavelengths. Okay, right from the ultraviolet to the radio. And now one important thing which I'll emphasize about, and from various missions. Okay, so you can see that many missions have looked at different windows. Okay, so the starting composition of Venus is important in respect of the rocks. Okay, and new insights regarding Venus are possible by carrying out in situ sampling, but it's extremely difficult because of the temperature and the pressure. Okay, that the lander has to survive before landing on the Venetian surface. But you have had Venera, which the USSR successfully landed, and then took some pictures as well. And from that, we know about these planes and the tessera. Okay. Now this is, now I'll go to moon. Okay. So now the permanently shadowed regions of the moon are have temperatures of the order of perhaps as low as 50 Kelvin, and therefore they can store volatiles. So volatiles are transported, from the warm sunlit regions to the polar regions. There is a theory of transport, and then these permanently shadowed regions can store volatiles for very long periods, for billions of years. And now it is believed that this is a major discovery. And one of course, Chandrayaan-1, the major discovery which I discussed is that Chandrayaan-1 M-Cube discovered water on the lunar surface, because earlier it was thought to be bone dry, and this has been confirmed by several other missions as well. L-Cross also, from part of the moon, it found that the water percentage could be as high as 5%. Now, it is believed that some polar hydrogen is present as water. I mean, one could argue that the neutron spectrometer experiment or the gamma ray spectrometer only looks at a hydrogen signal, but it has been found as water. It has been confirmed as water, but its distribution in the permanently shadowed regions is yet to be explored and will be carried out in future missions. And understanding the nature of moon's polar volatiles is very, very important in respect of the origin, timing of delivery, and subsequent evolution of water and volatiles in the inner solar system. Now, this is a paper from, this is some work which was done based on APXs of ISRO, Chandrayaan-3, and scientists from various various agencies from various institutes of ISRO, including PRL. PI is Santosh Wadwale, wrote a paper recently in Nature, which looked at the elemental abundances at the landing site, and this is showing you the traverse of the rover, basically, um, uh, and um, um, and the numbers you see are various locations where measurements were made by APXS, which is basically an alpha particle X-ray spectrometer. So there's an alpha source which basically excites, and then X-rays are emitted from the moon, and those are measured by an STT detector here. So therefore, now this is now these are the signals, the X-ray signals which I talked about. So you have many elements which are present on the moon, and you have K alpha lines as well as some K beta lines. And so there many important conclusions arose from this paper, very significant paper in Nature last year, and some of those are that it is the first ground truth in the south polar region of the moon, and there is homogeneity in the elemental composition which has been observed because it has been compared with other measurements as well in other areas. And Chandrayaan-3 site has SPA ejecta. This is South Pole Aitken Basin, which is a huge basin in the south polar region of the moon, and it is important in respect of its early impact activity, and is a mixture of ferron anorthosite. Fan means ferron anorthosite and magnesium type lower crust upper mantle material. So it is believed that it has excavated the mantle as well, South Pole Aitken Basin, and some of that material is presumably present in this landing site. So this was a very significant discovery, and material around the landing site possibly is a mixture of SPA ejecta and materials ejected by later formed craters, and this agrees with the basic ternary diagram which was shown in the paper when fan was mixed with magnesium soup minerals. Okay, some questions. So you may ask, okay, so this is done, what next? Okay, because the topic is about future. So now I have done 30 minutes. So Dr. Praveen, how much time do I have?
You may take maybe 10 more minutes.
10 more minutes. Thank you, Doctor. Yeah, thank you. So this curve is a curve. Basically, you are looking at the number of. Basically, this is impact flux, okay, as a function of age, and this needs the cratering activity needs to be calibrated based on radiometric dating of rocks which are returned from the moon. Now, as you know, there have been very few sample return missions after Apollo and Luna are not there. Okay, you have had orbiter missions from ISRO, now lander rover missions, but you haven't had sample return missions. But I believe it will happen in the near future, as was told by Dr. Das. So in this, you can see that there is a big gap, okay, in the central portion of that curve, and you need, basically, all I want to tell you is that we need missions which will bring rocks which are very old and also which are of intermediate ages between 4 billion and 1.5 billion years to fill this impact cratering curve, so that our crater counting ages are more reliable, because this is based on crater counting ages. All the other ages, even for that of Mars, are based on crater counting ages. So how has the impact flux changed? So let me throw some questions at you. How has the impact flux changed over the past billion years? What are the implications for lunar chronology? We need samples, okay? For this, we need a sample return mission. Can we obtain a lunar sample outside of that of the Apollo lunar explored regions? And particularly a sample of South Pole Aitken Basin ejecta, because we will understand the mantle if we do that. Did a lunar dynamo exist? So did we have a magnetic field which was comparable or a little bit less than that of the Earth, 0.4 Gauss level? So over the first 10 million year of lunar history, we need more simulations from Indian groups, and perhaps the South Pole Aitken Basin samples may address this as well. Where are the exposures of lunar mantle in the South Pole Aitken Basin? This also needs to be resolved. What do they reveal about the moon's interior structure? We need to assess distribution. This will be done soon, I believe. The distribution, characteristics, and abundance of polar volatiles, particularly in the permanently around the permanently inside the permanently shadowed regions, is difficult because solar panels, they're dependent on the sun, right? So, or you need development of RTG, which needs to be pursued soon. And do we understand how volatiles are transported over the surface of the moon? Now, this one is on Mars, okay? So this is Curiosity. This is this was a big rover. And let me just tell you that organics have been found. And if you find organics, there's a chance that they could have been habitable. So one needs to explore environments such as Gale Crater, where the climate has changed over time. Okay, so initially Mars was habitable, it was warm and wet, but then the climate has changed through time, and one needs to investigate these environments by sending rovers to these environments. Okay, so this I will just show, I will just flash, I will not discuss these. These are some questions which I put down for Mars. Then this is Vesta, okay? So this is linked to HED, but this was done following a mission, planetary mission, but we need other missions as well to different asteroids to link them to the meteorites, which have been studied by many groups within India, in particular PRL. And we need to see which of these contain carbonaceous chondrites, which is linked to life. You see carbon, maybe it is linked to life. So did life come to Earth from these asteroids? We do not know, frankly. I will skip this. And this is one way in which you can tell the time, the age of early solar system objects, okay? By making these isotopic measurements using a ion probe spectrometer. And okay, how many? Okay, I have 5 more slides, so I will go through these. So what is new? We do not know which asteroids have presence of water. Ceres has indigenous water, while Vesta's water is, so indigenous means inside, in the interior, okay? And exogenous means it has come from outside the asteroid. So does the time of accretion increase with distance from the sun? And therefore the amount of aluminium-26 present, aluminium-26 has a half-life of 0.7 million years. It is basically a heat source for large asteroids, okay? 10-kilometer size. Bodies. Now, did it decrease with thing? Then C, so carbonaceous, the ones which are rich in carbon, they are presumed to have water. Is this correct? Stony asteroids are dry. And then did they undergo internal heating, and was aluminium-26? Of course, this is still ongoing, the last question. So what next? Samples are essential. They provide ground truth and are necessary for, this is true for Moon, this is true for Mars, asteroids. and other objects as well. For high precision elemental isotopic analysis, detailed petrography and chronology investigation, missions should focus on interior of asteroids as well. So to understand the interior of the asteroid, and particularly using magnetometers, seismometers, and then water in asteroids inside the snow line. Do you have subsurface asteroid? We do not know. And organics as well. Okay, so this is the vapor plumes. This has been seen. This is picture credit and as listed to NASA. And Enceladus is Saturn's moon, and you know it's very interesting because the composition basically of these plumes was seen to have water. Okay, so therefore it is a site which needs further investigation and in future to look for the possibility of life. And I will not discuss about Titan. And the last two slides are on very important broad questions which need to be answered through future missions. How has the population of solar system bodies changed through time? What is the irradiation history for different solar system bodies? So in the initial part of the solar system, for example, for the moon, there have been many impacts. Okay, it has been bombarded, and you can see that on the lunar surface because there's no weathering there. There's no water or wind, right? So how did the interiors of solid bodies evolve? How are solid surfaces shaped by internal and external processes? How can we better understand the dynamics of atmospheres of inner solar system bodies? And why did planetary climates, for example, Mars or Venus, evolve to their current state? Does Earth share a similar climatic picture for the future to that of either of these objects? We do not know. Understanding the structure, evolution, and dynamics of giant planet interiors. This will come in. This will take some time. Its atmospheres, magnetospheres, and processes involved. The rings of outer solar systems. How did they form and evolve to their present state? For example, Saturn. Okay. So, and then regarding life. Okay. How did life originate on Earth? And is life likely elsewhere? What are the habitable environments in our solar system? How did they evolve to their present state? Can we discover signs of past or present life in the solar system beyond Earth? And this is just one slide. This shows you the interest in moon. Okay, just see from 2018. Okay. I have not listed the Apollo and lunar missions here. Just see the growing interest in moon because everybody wishes to go to the moon. And I can assure you there'll be the China, India, the US, and possibly Russia will be there on the moon. And Mars, of course, it is more difficult. So the Mars missions have a longer lead up time, and they take longer. But there is also interest in Mars, particularly the question of habitable environments. I will thank you for this, for your patience, and I thank the organizers again. This was a very interesting topic, and I hope I've thrown some light on some questions which can be addressed in future missions. And it is up to the students to take up engineering or mathematics in their future programs or physics and contribute to ISRO's planetary science program and planetary exploration program. Thank you.